to look at units first, right? Because unit is actually a fundamental part of physics. So at this point, it's very good to understand units, right? And how it can actually help you with any question that you have to answer, right? So let me, all right, so I'm going to use the board a lot. All right, everyone can see that, right? All right, great. All right, so the thing about unit that I would like to talk about is how do we use units in physics, right? Because we know that we have our SI units, which are length, or quantities, sorry, or fundamental quantities, which are length, mass, time, temperature, current, right? So we know we have these, which measures length measured in meters, mass in kilograms, time in seconds, temperature in Kelvin, and current in ampere. All right. So we know we have these, but we look at certain quantities, like let's say speed, right? And we know that speed has a unit of meters per second. So the first thing that a physics student should understand is what does this unit tells us, right? So if we have speed as a unit of meters per second, what exactly does meters per second tells us, right? Anyone who wants to give it a try? What exactly does ms to the -1 mean? Anyone? All right, so someone says meter on seconds. The speed is the length over time. All right, I like that one. So if we say that a car or an object moves at 10 meters per second, right? It's telling us that it's moving 10 length or distance over a specific time. Now, units, that's the purpose of units. So we can actually use it to describe the object or the quantity that we're looking at, right? So if it's for speed, it's moving 10 meters every second. So that's what the unit of speed tells us. But it also tells us that, all right, so someone is saying speed is the rate of distance in respect to time, right? And that's what we're going to look at now. How can we use the unit for a quantity to tell us something about that quantity that we probably knew, but we don't remember, or we did not know in the first place, right? So the unit here, which we know, M comes from length, right? And S comes from second. So we know that speed, right? Because we're at this level, everyone knows that the definition of speed is that it's the distance per unit time, right? But what if you did not know that definition, or you didn't remember that definition? We could use our unit to tell us that, right? Because we know that meters is measured, is a unit for length, right? And S seconds is a unit for time. So also we know that if it's per, then that means that it's being divided by. So it's a quantity that's measured in distance over a quantity that's measured in time, right? So we get distance over time. the distance per unit time. All right, so let's look at next one, which is, all right, let's use something that's a little bit harder. All right, so let's look at this one. So a unit that is J per kilogram per K, right? And at this, anyone know the quantity that this unit measures? All right, so specific heat capacity, great, all right? So if I should ask if you're in the first term of grade 10, right? What is the definition of that term with unit of that? I'm sure no one could actually figure it out, right? But everyone knows each of these units separately, right? So we know that G, the J here, is the unit of energy, right? So we know that J represents energy E. We know that kg represents mass M. And we know that the K there represents temperature T, right? So we know from this that because it's J per kg per K, it is the E over MT, right? So we have a quantity here that the equation is E over MT based on our unit, right? So everyone got that so far, right? All right, so if we are deriving the definition of this quantity, right, it's the amount of energy, right, that's is there per unit mass and unit time, temperature, sorry. So the amount of energy per unit mass per unit temperature, right? And if we know about specific heat capacity, it does actually state that the amount of energy required to raise 1 kilogram of a substance by 1 Kelvin, right? And that's what we have here. So a thing about unit is that we can describe the quantity, right? But we also can get a definition from our units, right? So we can use units to actually help us to get the definition as well as to get the equation for a quantity. Because I did this because when I did CXC, I wasn't taught this area of the syllabus, right? But the question gave the specific heat capacity of the substance, which let's say it was 100, right? So it said that C of the object is that, and they wanted to find the mass of the object, right? So because I could make the link between these quantities, so between these units that give us this, then I could know that C is equal to this, then I can make M the subject, right? So units can actually assist you with your examination, right? So that's a very good thing about using units to helping you deriving the equation or also to give you a definition for a specific term, right? So that's it for units basically, right? At CXC level, there is not a lot of units that you use with these, but I normally teach my students to just remember one. So you can remember the units to help you to define, or you can remember the equation to help you to get your units and to get your definition. Right? So physics actually can give you, is that easy that you can just remember one thing and you can get everything else from it. All right? So if you remember the equation, you can get the definition and you can get the unit. Right? So you don't have to be studying the definition, the unit, and the equation of a specific quantity. All right? So that's where units come into play. All right? So let's look now at the pendulum. All right, so we know the pendulum is any mass that is suspended onto a string that's allowed to swing freely. Right? So our setup of a pendulum normally looks like that. So we have the ball, the pendulum ball, we have a string, and we have the stand on which it is connected to. Right? So with this setup, the pendulum is a simple setup, laboratory setup, that's used to actually, one, manipulate certain quantities, right, and help us to actually measure specific quantities, right? So the first thing about pendulum that you need to know is actually define two specific terms, right? So the first term that you need to know is what's an oscillation, right? And the second one is your period or periodic time. All right, so that's where you come in. So what's an oscillation? Anyone? What's an oscillation? All right, so someone says an oscillation is the movement of an object from a specific point through a phase and back to that point. All right, so that's exactly what the oscillation is. So an oscillation is basically the back and forth movement from original position back to its original position. All right. So if we're supposed to look at the pendulum at this level, where it's actually displaced from its normal position right there, right? So if we displace it to point A and we allow it to swing, right? So we'll release it. It's going to swing over to its maximum point there and then swing back to A, right? So we call this B, then that's one oscillation. So it goes forward and then back to its original position. Or if you wanted to start the oscillation from here, right? So when you release it from A, it's going to go, let's use red. It's going to go forward to B, then it comes back to A, and then it has to come back to that original position, right? So it's the back and forth movement from a point back to that original position. So that's what an oscillation is. So it doesn't matter where on the movement of the pendulum you're looking at, it will still be the same, right? So it doesn't matter if you're starting from A, where it goes forward to B and then back to A, or you start from where it's in the center, right? So if you move it from A and release, you start counting from when it's here. So it will go to B, then from B to A, and then from A to its original position there, right? So that's what an oscillation is. And then the period or the periodic time would be all right, what's the periodic time?
Good night.
And then anyone wants to go with the periodic time? What's defined as periodic time or period? Alright, so it says the time taken for a pendulum to make one complete oscillation. Alright, so that's exactly what it is. So we just looked at what the oscillation is. So the period is the time it takes to actually complete that specific oscillation. Alright, so those are the two terms that you'd encounter while doing the pendulum. Right now, with the pendulum, right, we normally, when we're doing this experiment, we notice that we don't actually record the time for one oscillation, right? And that's because at some length, it's going to be hard for you to actually capture the accurate moment of just one oscillation being done, right? So we normally do it in the lab like 10 oscillations or 15 or 20 oscillations, so we can get a more accurate reading. So that's the reason why we do more than one oscillations when we're doing it in the lab. So it's to actually get a more accurate reading of the periodic time, right? So that's why we don't do just one oscillation and try to record the time for it, all right? Now with the pendulum, as someone in the chat highlighted, we look at the energy conservation between the ball moving from side to side, right? So we know that when the ball is displaced from A or B, right, it's going to actually attain its maximum potential energy at these points, right? And the reason for that is because it's being displaced to its highest position, right? And remember that PE is equal to M times G times H. So when we get this to be at its maximum, then PE would be at its maximum, right? So at these 2 points here, then your potential energy is at its max, right? And your kinetic energy would be at 0. All right, so we're moving from max potential energy, right? When you release it, it starts to move now. So that means at the center here, your kinetic energy would be what? What do you think? Max or equal to your potential? Oh, this is the same mg delta H right here. So that's the same. All right, anyone? The max? Sorry, someone says the max. Anyone else? What do you think the kinetic energy will be at the original position? PE equals KE for someone. All right, so at the center, it's KE would be equal to your maximum speed, your maximum energy of KE right there. All right, but what this means though is actually it's equal to your PE as well, right? So ignoring air resistance at the original position, your PE and your KE is equal. But the important thing is to note that your KE at your original position is always equal to your maximum energy, kinetic energy at that point. All right. So back to the potential energy, the delta H. What the delta H symbolizes is that when the ball is at its original length like this, right? It's that we know that it has a height of 0, right? So when we displace it here, it's going to actually get a new height. So that change in height there is this right here. So you can use change in height or height. It's the same for both once you understand, right? So it's the change in height from when it's not, when it's in its original position to when you displace it to a new position. So that vertical height there is your change in the height to finding your potential energy. All right? So, and the last thing for pendulum would be the factors that affect how fast or the time for the period. So the periodic time. So what are the factors that affect the periodic time? So let's go. Who wants to give some? So what factors affect the time in which it takes for the pendulum to swing? So one person gives length and mass. All right, so the length. So if you increase the length, then that means you're increasing the time in which it will take for it to complete a complete swing, right? And the reason for that is because it's actually going to move a further distance away. So we notice the movement is like an arc, right? So the longer the string, the more arc distance it's going to cover. So that's the reason why the distance will be longer. So the time will take to complete it will be longer as well. So if it's a short distance, so from here to here, right, it's going to move a shorter distance for that swing. If it's long distance, it moves a longer distance for the swing. So that's why the time is increased as well. The angle of displacement is the next, right? So the angle at which you displace it from its original position, which is at this point there, theta, right? But that angle is important, right? What's important about ensuring that? Why is it important that the angle there should be a very small one? If we get it big, what's going to be the main problem that you're going to face when the angle is big? Anyone? What problem will you face if your angle that you're using is a big angle? The period decreases. Well, yes, but that's not the problem that you're going to actually experience. So a problem that you're going to experience if the angle is big is that the pendulum will not have a smooth swinging, right? So when your angle is big, your pendulum, when it starts to swing, will start to actually move in a circular motion, or it moves in this path, right? So if it's supposed to move like this, right, over a period of time, it's going to actually move forward until you start seeing it moving, changing direction like this, right? So that's the problem with using very high theta values, right? So we normally have like between no more than 10 degrees, right? So the larger the angle gets, the more it will actually start going out of, of its oscillation path, all right? So that's all we need to know about the pendulum, right? And we know the equation for pendulum is that T is equal to 2 pi square root of L over G, right? So that's your equation for pendulum. That shows us that the periodic time and length, they are directly proportional to each other. So once you increase the length, your time also increases, all right? So the next topic on the agenda is some more calculations now. We're going to look at the density. All right, so someone asks, when do I use the formula? All right, so the formula, using this formula is important, especially when it comes to plotting a graph, right? So let me just look at that for a little. So CXC will never ask you to use this equation to find the periodic time or the length of a pendulum, right? But they would use this graph to help you or to ask you to say, if you have a table, right? We all know the table of the pendulum, but they ask the question to say plot t squared versus length, right? So that's part A, and then part B they would ask you is to calculate G, right? No, more than likely they would ask you to find gradient, calculate the gradient, and then they would ask to calculate G. All right. So this is where the knowledge of the formula comes into play. All right. Because first we have to know that if we're plotting a graph of t squared against L, right, then that means we need to ensure that this formula resembles what we're plotting, right? So because it's t squared and it's L, it's not the square root of L or t. That means we have to make t squared and L be in this formula there, right? So all we're doing is squaring both sides. So if we square both sides, right, then we get t squared will be equal to 4 pi squared L over G, right? And that's how most books will have it, right? So we know now that the t squared here represents what's on your y-axis, right? The L represents what's on your x-axis. And the important part now is that the 4 pi g here represents your gradient f, right? And we know that because y is equal to mx plus c. And it's a straight line graph, so that means that's your x, that's your y, whatever is beside the x is your gradient, right? So your gradient would represent 4 pi squared over g. So when you calculate your gradient, then you use this part here to say that m gradient is equal to 4 pi squared over g. And then from that, you can find g, because now you have your gradient value, and you substitute pi for 3.14, right? So that's how you use the pendulum equation. So at the CXC level, that's all you need to know. But more, they always give you the formula. So it's not that you have to revise the formula, but you need to know that to make the link that if you plot t squared against L, then the 4 pi g, the 4 pi squared over g, represents your gradient value, right? So they always ask you to find a gradient, and then they ask you to find the value of g. All right, so did that answer the question? All right, so are we following that? All right, so let's move now to the next thing on the list, which is density. All right, so with density, we're going to look at two same size objects. All right, so they're the same size. All right, so they're the same size, and the circles here represents the masses. Right, so this is object A and object B. All right, based on our knowledge of density, what's the difference between A and B? Anyone? What's the difference between object A and object B? Noting that both have the same size. Particles are packed tightly in A. All right, so someone says particles are packed tightly in A. However, B is dispersed. Anyone else? Or is the same? All right, same answer. All right, so exactly. So we know that A particles, the masses, they are compact together, right? While B, the masses have more spaces between, right? And that tells us the density of the object, right? Because they are of the same size, they are of the same size. So because this has the masses compact together than B, then we say that A has a higher density than object B, right? So density tells us how closely the particles or the masses in an object are with each other, right? So if it's the same size objects and it has a different density, then the one that has the higher density has its masses closer together, while the one that has a lower density has its masses further apart, right? And so that's with density, all right? So another thing about density is that we need to know the formula. And we know that density symbol is rho, and rho is equal to mass over volume, right? So mass over volume, which is the amount of masses in the object over the volume of the object itself, right? And then we look at the unit. So what would be the unit of density based on our quantities? Right? So based on the quantities, what's the unit? Kilogram per meter cube or grams per cm cube. Right? So we know that density is kilogram per meter cube or it's gram per cm cube. All right, and we know that because mass is measured in kilograms or grams, and volume is measured in meters cube per or centimeters cube. Now, the thing to note about these two units is that this is your SI unit 1, right? But CXC also would use this one as well. So if it asks you for SI unit, you only use this one, right? If it didn't specify, then you can use any one that's there. So another thing is that if you're using mass in kilograms, you'd have to use volume in meter cube. If you're using mass in grams, then you have to use volume in centimeter cube, right? So guys, the video is going to actually start, is going to stop because it's the 40-minute difference or time limit. So I'm going to restart now, and then we come back to using this formula to do some questions. All right, so it says a rectangular block of material of relative density 2.0 has the following dimensions: 10 centimeters by 80 centimeters by 2.0 centimeters. Calculated volume in centimeter cube, millimeters cube, and meters cube. All right, so because we didn't talk about relative density before, Let's look at relative density before we attempt that. So we know that relative density is the density of the object over the density of water, right? So it tells us how much more denser an object is more than water. So this is one way how we can actually explain why objects float and sink in different liquids, right? So even though this is water here, if it's another liquid that the question will entail, then you'd use that liquid density here, right? But because we normally use water as a base for objects floating, then the equation has it specific to water, right? So it tells us if an object will float or sink in water, right? So the relative density we know is dimensionless, meaning that it doesn't have a unit, right? And the reason for that is because we're dividing two objects that are of the same quantity. So we're dividing density by density, so their both units will get cancelled out, right? So that's what dimensionless means. So if the relative density is greater than 1, right? So if we calculate that it's greater than 1, then the object will actually sink, right? And if the relative density is less than 1, then the object will float. So that's one basis how we know if objects will sink or float in a specific liquid. If we calculate the relative density and it is less than 1, then it floats. If it's greater than 1, then it's going to sink, right? So now with that knowledge, let's look at the first question here. All right, so it says the relative density is 2. And so in this case, it's going to use water as the base. So we know the density of water is 1,000 kilogram per cubic meters, right? So if it says that the relative density is 2, so that means R rho is 2, we have relative density of water, right? Then it asks us to find the volume, but we don't need to do all this because it's just the volume they're asking us to find. So we have length being 10, sorry, width being 80, and the height being 2.0. So therefore the volume will be length times width times height, which is 10 times 80 times 2, which is, and this is a unit of centimeters cubed. All right, so that's the first one. All right, so that's part 1. Part 2 says in millimeters cubed. So in millimeters cubed, the easiest way would be to change these units to millimeters, right? And how do we move from centimeter to millimeters? Anyone? How do you move from centimeters to multiply by 10? So exactly, so we multiply each by 10. So we get 100, multiply by 10, we get 800, multiply by 10, we get 20. Right? So part 2, the volume will be the length,
Yeah.
which is 100 times 800 times 20, and that is equal to
Like all the backgrounds out in the car.
all right, and we get 1.6 million millimeters cube. And the final part is in meter cube. So in meter cube, then that means we need to change the centimeters now to meters. And to change from centimeters to meters, how do you move from centimeters to meters? All right, so someone gave me the final answer. Before we move to the final answer, just want to check, how do we move from centimeters to meters? One, we divide by 100. Divide by 100. All right. So in these cases, we divide by 100. So divide 10 by 100, we get 0.10. Divide 80 by 100, we get 0.80. And 2 by 100, we get 0.02. Right? So in this case, it would be 0.10 times 0.80 times 0.02. And the answer there would be 1.6. We get 0.0016 meter cube. All right, so let's look at something that most students will get wrong. All right, so because it was already in centimeters, everyone I think will get this right. But because students normally want to find the easy way out, they're not going to do this. Right, so they're not going to convert each unit to meters cube and then do this, millimeters and then meters and do that. They're going to use this and use the principle that they know that says to move from centimeters to millimeters, we multiply by 100. So what most students would do is this answer for centimeter cube, they would just multiply by 100 to get millimeters cube. But we notice that if we multiply this by 10, by 10, we're not going to get 1.6 million, right? So the problem is that we're not looking at the feature that says that 1 millimeters equals 10 centimeters. So if we're moving from millimeters, but remember we're looking at cube, so that means if we're cubing this side, we have to cube this side as well, right? So that tells us that 1 millimeter cube is equal to 10 cube, which is 1,000, right? So if you know this reference, then if you find this one, then you can just multiply the 1,600 by 1,000, and we get the 1.6 million, right? So that's the easy way of moving from centimeter cube to meters cube by multiplying it by 1,000. And hence, if we need to do it by millimeter into meter cube, from centimeter cube to meters cube, right? Then we know that 100 centimeters equals 1 meter. So if we're cubing the centimeters cube, we have to cube this side too. So we get 100 cube, which is 1 million. So it's 1 million centimeter cube equals 1 meter cube, right? So that's the difference. So we have 1 million centimeter cube equal 1 meter cube. So because we're moving from centimeter cube to meters cube, we divide. So in this case, we divide by a million, right? And if we divide by a million, we get that there, right? So that's the relationship that most students will get wrong, right? So if we're changing from centimeter cube to millimeter cube, is not just multiplied by a 10, we're multiplying by 1,000 because it's 10 times 10 times 10, right? And if we're moving from centimeter cube to meters cube, we're not dividing it by 100, we're dividing by 100 cube, which makes it a million, all right? So everyone got that? All right, great. All right, so part B says no. What's the density of the material of the block in gram per cm cube and in kilogram per cm cube? All right, so now we're going to use this part up here. All right, so we're finding the density. And we're given the relative density and we know have the volume. All right, so we know to find the density of the object, since we have relative density, so density of object will be equal to the relative density times the density of water. Right? So from that equation there, so we have the relative density from the question, which is 2, times the density of water, which is 1,000. So we get 2,000, and this is in the unit of kilogram per meters cube, because that's the density of water that we use. Right? So that's the second part. So the first part, right, is the same because the density of water in grams per cm cube is 1 gram per cm cube. Right? So for the first part, it's the same. So the density would be the density, relative density times the density of water. So we get 2 gram per cm cube. Right? So this is something that we need to look at as well. So gram per cm cube is normally a smaller number than the kilogram per cm cube, right? So because the density of water in gram per cm cube is 1, then the density of water in kilogram per cubic meter is 1,000, right? So if we work out the first one, right, which is gram per cm cube is 2, to find the relative density, all we're doing is just multiplying the number by 1,000, right, to get it in kilogram per cubic meters. So that's how you move from grams per cubic centimeter cube to kilogram per meter cube. All right, the last part of the question that's related to density is what's the mass of the object in grams and also in kilograms. Right, so let's look at it in grams first. So we have the density, which is 2 grams per cm cube. So we know that density is equal to mass over volume. So therefore, the mass is equal to density times volume. So the density is 2 because we're looking at it in grams. So we have to use the one that has gram in it. So it's 2 times the centimeter cube volume, which is 1,600. So we get 3,200 grams. Right, so that would be your mass in grams, right? And then your mass in kilograms, because we don't have to work it out because we know the relationship between grams and kilograms, right? So it would just be that it's 3,200 over 1,000, which is 3.2 kilograms, right? So that's how we work it out. All right, any questions? All right, second part, what equation did you trans this part? All right, so it's this equation here. So we use relative density equal density of object over density of water. So we find the density of the object, so it's relative density times density of water. That's this and this right here. So that's part B of the question. All right, everyone understand? So we can move on to another question. All right, so let's see. All right, so let's look at this and then we can fully get density. All right, so distinguish between density and relative density. So who wants to take a shot at that one? Yes, who wants to distinguish between density and relative density? All right, so someone says density is the mass of an object against its volume, while relative density is the density of an object against density of water. Another person says density of a substance is the mass per unit volume, while relative density is the ratio of the density in reference to another, usually water. Right, so both responses are indeed correct. Right, so density of the object tells us how compact the masses are, which is the mass per unit volume. And the relative density tells us how much more denser an object is, more than a base density, which is usually water, right? So that's the distinction between both density and relative density. All right, to show why relative density has no unit. All right, so in this case, to show that it has no unit, all you do is to just use two numbers, right? So we know that relative density is the density of object over the density of water. So we use density of object. So let's use the first one to be this, and then let's use water, which is 1,000 kilogram per cubic meter, right? So we know, so in that case, we will just cancel the units because they're the same, and then we get an answer of 1.6. So we notice there is no unit, right? So that's how you show if it has unit or not. We just put two numbers with the same units because they're the same density, right? And we show that both units cancel, so we're left back with a quantity that has no unit. All right. All right. So next part is a block of wood measures 2 centimeters by 4 centimeters by 9 centimeters. Calculate its volume in SI units. All right. So we know the SI unit of volume would be in what? What unit would we calculate this in? Centimeters cube or meters cube or millimeters cube? Which unit are we working with? Our meter cube. Great. So meter cube would be the unit that we'll be working out the volume in. Right? So in that case, let's do it the longer way. So first we're going to change all those centimeters to meters. Right? So we change in 2 centimeters to meters, which is divided by 1,000. So by 100, sorry, we get 0.2 meters, and it's 4 centimeters to meters, 0.04. And the last one is 9 to meters, which is 0.09 meters. So we know that volume is length times width times height, which is 0.02 times 0.04 times 0.09, and we get please double check this and see if this is the answer. Yeah, so we get 7.2 times 10 to the negative 5 meter cube. So that's the answer for that part there. All right, so we already did it in standard form for the second part. So and then it says if the mass is 57.6 times 10 to the negative 3 kilograms, calculate its density. All right, so we know now that density is equal to mass over volume. So the mass given there is 57.6 times 10 to the negative 3 over the volume, 7.2 times 10 to the negative 5, and we get and we get 800 kilogram per cubic meters. please note again, the volume is in cubic meters, sorry, and the mass is in kilograms. So that's why we can just both divide to get our unit in that, right? So that's it for density. All right, so that's it for density, a very simple one. All right, so it doesn't get harder than this for density. All right, so now let's look at vectors.
Obey.
All right, so looking now at vectors and scalar quantities. All right, so we should know the definition of vectors, quantities, and scalar quantities. All right, so anyone wants to try? What's a scalar quantity first? Scalar quantity, anyone? It's a scalar quantity, magnitude but no direction. Scalar quantities only have a magnitude but no direction. All right, so we do understand scalar quantities, right? And we know that magnitude represents the size, right? So what that tells us is we know that time is a scalar quantity. And if we record time, if we do something in 60 seconds, right? So we only represent time by writing your size or your magnitude and your unit, right? So size and unit is only for scalar quantities, sorry, for scalar quantities. So you have the magnitude, there is no direction, right? Because time has no direction pertaining to its quantity, right? And then we know that vector quantities has both size and direction, right? And someone gave other quantities for scalar, which is mass, distance, time, density, right? Are all scalar, right? And then vectors now, we can start writing some for vectors, right? So let's use force. So we know force, if we say 10 newtons, right? So the size is 10 unit newtons. Now the direction, how does the direction come into play, right? But if you're saying that you're pulling a bag of 10 newtons, then the direction means that the direction is a pull, right? Or it can be a push, or it can be a twist, right? So those terms will actually specify the direction in which you're going, right? Now, another thing for direction of vectors we use is that we can use a plus sign, right? Or we can use a negative sign. And those negative and plus does not mean that the number is, or negative mean that is less than zero, right? It just gives you the direction. So with a plus, right, we always use a graph, a t-graph to show. So anything that is plus means that it's either going to your right or it's going up, right? So plus any vector that is a positive number means it's going to your right or it's going up. If it's negative, that means it's going down or it's going to your left, right? So that's what the negative and the positive in your direction means, right? And we're going to use this a lot in physics. So going to the right, right? So if you're having, so if you have an object that's moving in your x-plane, it has a negative velocity, then that means it's going to your left, right? If something is falling and it says its velocity is -10, then that means it's coming down, right? So that's important for future use. That direction normally in physics is given by positive or negative, or we can use angles, right? So we can use angles in reference to your direction. So just like bearings in math, you can use angles to determine your direction of quantities in physics, all right? So now that we know, all right, so some persons for vector, we have displacement, we have force, acceleration, velocity. So all those are vector quantities, all right? So let's now look at the hard part for some, which is resolving your vectors, right? So resolving your vectors to get a resultant vector. Because we know that a resultant vector is just one vector that gives you the magnitude of two or more vectors that is active, right? So if we have a box here, and we have two forces pushing on the box, we have 2 newtons and 5 newtons, then the resultant of the box would be that the box is experiencing a force that is 5 plus 2, which is 7 newtons, right? And it's going in the same direction. So when it's going in the same direction, we add our vectors, right? And then if we know that if it's going in opposite direction, so if the 5 is going that way, and the next person pushing here with a 2 newton, then the box would experience a net force going in that direction of the larger force, right? And in this case, we minus to get 3 newtons, right? So that's what the resultant vector tells us, right? What's the outcome of 2 or more forces or vectors on a specific object, right? And it's easy when they're in parallel to each other. So if it's going in the same direction or it's going in opposite direction. But what if the velocities or the vectors, right, are going at an angle to each other, right? So we're going to look at when the vectors are acting at 90 degrees to each other, right? And at 90 degrees means that if we still have a box here, we have the 2 newtons and we have a 5 newton, right? So we notice we have 2 newtons pushing to the right and we have a 5 newton pushing up, right? So in this case, to find the resultant, right, because just logically looking at it, if we have 2 persons pushing like this, the object will tend to actually move in a slanted manner like this, right? So in physics, we'll explain how exactly where the object will be moving, going that way, and also the size of the force that it will be moving with, right? So in this case, we're going to resolve this vector by using the triangular method, right? And the triangle method tells us that we're going to create a right angle triangle. So the first part is to connect. So we connect both vectors, head and tail, right? Without changing their direction. So that's important. So in resolving those vectors, we ensure we connect these vectors without changing their direction, right? So in that case, if we connect, So that means we just ignore the object, right? And let's draw the first one. Let's say this is your 2 Newton force, right? So it always have to be going to your right, right? And then the 5 has to be going up. So that means we can put the 5 here, right? So that's a head to tail connection there. Or we can put the 5 here, which is a head to tail connection, right? So in both cases, it's right. So therefore, if we connect both these 3 ends now, right? We notice both these resultants are going the same direction, right? So it doesn't matter if you draw your triangle here or here, you're still going to get your same answer, all right? So let's use the bottom one. So we have that, and that is our resultant R, right? So we notice that this is a right angle triangle now, so we can use Pythagoras theorem to find R, which is the square root of your sides squared, right? So it's 5 squared is 25 plus 2 squared 4 is square root of 29, which is 5.39 newtons, right? So that's your resultant force on the object, right? So we know now that the force that's acting is 5.39. Now we need to know what direction it's actually going in, right? So to do the direction, we use the angle that's at the tail of your resultant, which is that angle there, right? So we're finding the angle. We have all 3 sides, so we can use any one. Let's use tan for this one. So tan theta is your opposite side, which is 2, over your adjacent side, which is 5, right? So theta would be your tan inverse of 2 over 5, which is 0.4, right? So therefore, tan inverse of 0.4 is 21.80 degrees, right? So this here would be the angle that the resultant vector is moving. So I normally write a statement that says that the resultant R is 5.39 newtons. That's acting 21.80 degrees away, and this angle is acting away from our 5 Newton vector. Right? So that's our final statement that gives us your magnitude as well as your direction in which your resultant is going. All right, so I'm going to actually put one here for you guys to do and tell me where. All right, so go over from time. I'm not sure if I get where you're coming from time. Could you specify where you were lost, please? Two or five. Oh, no, tan theta. Oh, okay. Oh, yeah, I'm seeing that clear as well. Well, you're not going to see if I turn off the light. All right, so let me put it here. All right, so what's here is your angle, which is, we're going to use tan theta, which is your opposite angle, which is 2, over your adjacent angle, which is 5. So we have theta being tan inverse of 0.4, right? And we get 21.80 degrees. So that's the angle that's there. Yes, so our resultant now will be the size of the vector force, sorry, and the angle. So it's acting this, and that angle is away from your 5 newtons vector. All right. All right, great. All right, so I'm going to leave this one, and you guys can do it now and tell me what you got for your answers. All right, so we have an object here. We have a push of 4 meters per second, right? And we have this one here going at 3 meters per second. All right, so I'll give you 5 minutes to work that one. All right, 2 more minutes, guys.
They look so real.
Anyone with the answer so far? All right, so I'm seeing Brianna says 5. All right, so what's the angle, Brianna, for your 5? All right, so 53.13. And which one it's acting away from? Acting away from the 4. Are you sure? Are anyone else got anything different from that? All right, so let's justify yours and see. All right, so someone else got 5, acting 53 away from 3. All right, so let's see which one is right or both. All right, so the first thing we do is to sketch our diagram, right? Without the object, so head and tail. So let's go with 3 going down, right? And then we need 4 to be going to the right. So we can put 4 to the left, sorry, 4 here. So that's head and tail connection there. So we get R to be going that way, right? So it doesn't matter if it's this way or if you drew it this way. Right? If you drew it this way, it's the same as this way as well. Right? So therefore, r is equal to the square root of 4 squared plus 3 squared. 4 is 16, 3 is 9, square root of 25, which is 5 meters per second. Alright? So I think everyone got that part right. So let's do this triangle first. So remember, we're doing it from the tail of your r. The theta is that one, right? So let's use something else otherwise from tan for this one. So let's use sine. So sine theta will be your opposite sine, which is 3, over your hypotenuse r, which is 5. The theta is sine inverse of 3 over 5, which is 0.6. And we should get 36.87 degrees. Right? So we get that. So we write that r is 5 meters per second, acting 36.87 degrees away from, and it's acting away from the 4. Right? So let's look at if we had used this one here. So the theta will be right here, right? And let's use sine again. So sine theta is equal to the opposite, which is 4 over hypotenuse 5, right? So theta is sine inverse of 0.8. And this you get to be 53.13 degrees, right? So you notice these two are different angles, right? But it depends on how you draw your diagram, right? Now, this is where it's going to get tricky. So remember, this one was acting away from the 4. If you found 53, then 53 is acting away from your 3, right? So that's the difference. So if you got the 36, it will be acting away from the 4 because you use this triangle here. If you got 53, then you use this triangle, which means that acting away from the 3. Alright? So that's where it gets tricky. Alright, so everyone got that? Alright, so I hope everyone got all those things from vectors. Alright, so we have 20 more minutes. Alright, so I'm not going to go through any more from the checklist. We have, forces and moments to cover. We'll do that next class. Right, so what we're going to do now is going to look at some past questions, some multiple choices. So roughly 20 or 10. All right, so 10 questions from 3 past papers, and then that will be it for today. All right, so here we go. All right, so this is 2002. All right, so the first question is something that we just did. All right, so you guys will be giving me the answers. Let's go, question 1. It says, which of the following physical quantities does not have a unit? So A is refractive index, B is EMF, C is density, D is frequency. All right, what's the answer that we have? Refractive index, someone said. All right, so that is refractive index. All right, so that's A for refractive index. All right, question 2. The base unit of temperature of the SI system is A, degrees Celsius, B, degrees Fahrenheit, C, Kelvin, D, degree centigrade. C, great. All right, so C is our answer, Kelvin. All right. All right, great. So 3 is about density. So the mass of a piece of metal is 43.7 grams and its volume is 5.6 centimeters cubed. A student uses a calculator to find the density of the metal and obtain the figure 7.803571. You should write the density as all right. So which one of those would he write the density rounded off to? All right, someone says C. Do you agree with that? All right, and we'll go with C. All right, so it's C because if we have two quantities that are to 1 decimal place, then that means your answer that you get should also be to 1 decimal place as well. All right, so that's how physics calculations are. We always work with our decimal places. So we have 1 decimal place for both. So therefore, answers should be rounded to 1 decimal place. All right, so a pendulum question. So a simple pendulum oscillates about center O between positions X and Y. Which of the following should represent one oscillations? The arrows indicate the directions. All right, so which one of these represent your oscillations? One oscillation. All right, so LeBron says C. All right, person is saying A. All right, so let's look at A. So A says it's one only. So X and Y would be your extreme positions, right? So X and Y. O is in the center, the origin, right? So it's moving from X, passes O to your Y, and then from Y passes O to your X. So it comes from, starts at X and ends at X, right? So that's one oscillation. So 1 is correct, right? But let's look at 2 is also correct. So remember, it's always in the center. So it moves from O to X, all right? And then from X, it moves back to O, and then it moves to Y on the next side, and then back to O. So we notice we started at O and ended at O, all right? So it's also an oscillation. And Y, and for part 3, it goes Y, O, X. So you notice there is no Y, it doesn't reach back to Y again. So therefore 3 is not a part of it. So therefore we notice that 1 and 2 is a part, so the answer is C. All right, so remember oscillation means where it starts, it goes forward and comes back to that starting position. So 1, it started at X, went through to Y and then back to X. All right, and then for 2, it started at O, it went through, passes X, comes through Y, and then stop back at O. So therefore, both 1 and 2 would be at one oscillation. So we have that as an answer as well. So it's 1 and 2, which is C. All right, everyone got that? All right, great. All right, question 5. All right, we're going to skip question 5 and look at 6. When X equals 0, the value of Y is, all right, so which one of these show us when X equals 0, what Y would be equal to? Oh, we're not doing number 5 because that's not a part of what we did today. So we'll go back through that when we finish with those topics. All right, so what do we have for 6? When X equals 0, then Y is equal to P, Q, S, or P over R. Which one of those? B, S, yes. So when S equals 0, X equals 0, sorry, that means there is no X value. So that means only thing on your Y would be the values, and the graph cuts the Y axis at S. So therefore S is your answer, which is B. All right, so 7. All right, so we didn't do forces as yet, so we're going to leave that one. So let's look now at this paper, which is 2003. All right, so we haven't done electricity as yet, so we're going to skip that. So question 2, which of the following is not a fundamental quantity? All right, so which one is not a fundamental quantity? Temperature, heat, energy, length, or time. All right, and we got exactly B, which is heat energy. All right, so not a fundamental quantity. All right, next. Figure 1 shows a measuring cylinder containing a fixed volume of liquid. Figure 2 shows a solid mass body submerged in the liquid, in which case the total mass of the container and its content is indicated. The density of the solid is, all right, so we notice without the solid in it, the volume is at 30, and when the solid is placed, the volume moves to 50. So that means the volume of the stone would be 50 minus 30, which is 20 milliliters, right? And we notice the mass change from 100 grams to 160 grams. So therefore, the mass of the stone would be 60 grams. So if we need to find the density, density is equal to mass 60 over the volume. All right, so it's milliliters, and 20 milliliter is the same as centimeters cubed. So 20 milliliter is the same as 20 cm cubed. So therefore we have 60 over 20, which is 3. So therefore your answer would be C. Exactly, C. Which of the following is suitable for measuring the diameter of the human hair? So measuring your hair, tape measure, vernier caliper, micrometer, screw gauge, or the meter rule. C, micrometer, screw gauge. That's correct. All right, so the micrometer screw gauge is used to measure the diameter of very small thickness, like your hair. All right, so tape measure is not appropriate. Vernier caliper is too big for that, and the meter rule definitely can't work. All right, next. 3 immiscible liquids PQR have densities which differ. Q is denser than P, but less dense than R. Which of the following diagrams show how the liquid settle in the measuring cylinders? All right, so based on this, the statement, we have Q is denser than P, right? But less dense than R. So obviously R is the densest, right? So R is the densest, P is the least, and Q is between. So therefore, we have A being our answer. Right, so for 5, A would be the answer. R is the densest, P is the least densest. All right, we just did this one before. All right, and those we haven't done as yet. All right, so let's look to the last set. And we start with question 2. 1 gram is equal to how much milligrams? So 1 gram is equal to 1,000 milligrams. Yes, that's correct. All right, not going to do 3, not going to do 4, because we haven't done those as yet. All right, 5, which quantity is dimensionless? Just looked at this. The answer there would be C, yes, relative density, right? Has no units, so it's dimensionless. We just did this one, right? So remember it was OS for P. All right, so that's it for the topics that we did today. All right, so next class we will continue from where we left off and additional things, hopefully. All right, so I hope you guys learned something today. All right, and I'll be uploading this lesson to the channel so other persons can see, or you can actually go back and look on things that you didn't catch while we were going through. All right, so also I'm going to give you the channel's email address. So if you want any information or past papers, you can actually email me so I can actually send them to you. All right, so there you go. So that's the email address that you can use. You can email me and I can actually provide you with any information that you'd like for physics. All right, guys, so that's it for today. Thank you very much, guys, for availing yourself for this lesson, and see you guys next time.